Hi and welcome to a lesson of partial differential equations. So in today's class, we are going to discuss a different decomposition method from Adomian decomposition. So actually it resembles the Adomian decomposition, but in a sense, it is somewhat different. So unlike in Adomian decomposition, what we did is we apply uh, LT inverse operator or LX inverse operator onto the equation. But in this decomposition method, what we will do is we will apply both the operators simultaneously onto the equation, right? And then we will expand uh, the equation and arrange the terms and then simplify to get the solution. So let us start with applying the inverse operators, that is LT inverse and LX inverse on both sides, since the differential equation is linear and it is containing the first order partial derivative with respect to t and second order partial derivative with respect to x. So the LX inverse operator is the integral, that is the iterated integral from 0 to x, and LT inverse operator is just a single integral from 0 to t. So we have applied the inverse operators on both sides. Therefore, now we can expand by solving this problem. So since now one thing that we need to consider here is that we can interchange the operators based on the knowledge that the problem satisfies the Lipschitz continuity condition. So we can interchange these operators since it suggests that the solution we are going to get is unique and it's continuous and its partial derivatives are also continuous, right? Now when we apply this inverse operator here, so uh, if we apply LT inverse on UT operator and keeping LX inverse operator, so we can write in this way: LX inverse applied on LT inverse applied on U. So LT inverse applied on U gives UXT minus UX0. And on the right hand side, first we'll apply LX inverse operator, keeping LT inverse outside. So LX inverse applied on UXX gives UX comma T minus X times UX 0 T, and then minus U0 T. Then we have negative 3U. Therefore, we can simply write negative 3 LX inverse U. No need to expand this. And then plus 3 LX inverse applied on the constant one, right? Now we can see here that we have UXT term here, UXT term here, and then this UXT term here. So we can just combine all these on one side of the equation. Therefore, let us combine this on the left side. So we get LX inverse minus LT inverse minus, now this is 3, this is negative 3 LX inverse UX comma T, and LT inverse is applied on all of this. So we can write negative 3 LT inverse LX inverse applied on U equals, shift this to the right side, we get LX inverse UX comma 0, then minus LT inverse applied on X, and let's say this is function of t, so this is h of t, so this is x h of t plus this u of 0 comma t is given as 1, so we'll write 1 here, And then we have LT inverse applied on this here. So this positive LT inverse, LX inverse applied on 3. Now we can shift the operator that is on the left hand side to the right hand side in the denominator. So this is somewhat kind of the operator D method that we have been using in the topic of differential equations. So now u of x comma t can be written as 1 over Lx inverse minus Lt inverse plus this is plus 3 Lt inverse Lx inverse, and now here we have this function Lx inverse applied on ux comma 0. So Lx inverse applied on ux comma 0 minus Lt inverse applied on x h of t plus 1 and plus Lt inverse Lx inverse applied onto 3. Now if you take Lx inverse common here and take it to the numerator, so let's see what we will get here, and the problem will be pretty much simplified. So now we can move this to the numerator by taking out common. So this becomes Lx over 1 minus Lt inverse Lx plus 3 Lt inverse u equals applied on this one Lx inverse ux comma 0 minus Lt inverse x h of t plus 1 plus Lt inverse Lx inverse applied on 3. Now we will simplify this function on the right hand side. So now we can see that when this Lx is applied onto this whole function, so here we have Lx inverse, so we are only left with u of x comma 0. Just let me write it like this. U equals 1 over 1 minus Lt inverse Lx minus 3 Lt inverse, and this Lx is applied here, so we will left with the ux comma 0 because Lx applied on Lx inverse it cancels and we get the function only. And then here we have the function h of t with x as a multiple and plus 1. So when Lx is applied on this function, it makes it 0 because this is second partial derivative and this will become 0, therefore this term vanishes. And then here we have plus Lx applied on Lx inverse, and this cancels, so we are left with Lt inverse applied on 3. Now shift this denominator into the numerator, so we can write it in this way: Lt inverse whole to the power -1, and ux comma 0 is 1 plus sine x, plus this will be 3t. Now one thing we need to know is that the series expansion of 1 plus, sorry, it's not 1 plus, it's 1 minus. So this is 1 minus x inverse is equals 1 plus x squared plus x cubed and so on. Therefore, we can now simplify this thing here. So we can write it as u equals 1 plus LT inverse LX minus 3 LT inverse plus LT inverse LX minus 3 LT inverse squared, and so on, applied onto this function, that is 1 plus sine x plus 3t. Now let us expand this whole function. So we'll get u equals, when this 1 multiplies with this, we get 1 plus sine x plus 3t, then plus, when this operator, that is LT inverse LX minus 3 LT inverse, is applied on 1 plus sine x plus 3t, what we are going to get is, when this is applied here, Lx is applied, so 1 goes to 0, 3t goes to 0, sine x, we have negative sine x, and LT inverse gives t, then minus this 3 times LT inverse, it gives minus 3t, then we have minus 3t sine x, then we have negative t squared over 2 factorial. So we write it here that negative 3t negative t, which gives negative 4t sine x minus 3t minus 9t squared over 2 factorial. All right, now we have the second term, that is the squared term, which means that let us now this LT inverse Lx minus 3 LT inverse squared is applied on this function, which means that we can write this as LT inverse Lx minus 3 LT inverse is again applied on LT inverse Lx minus 3 LT inverse is again applied on the function 1 plus sine x plus 3t, and this result we already have, that is this part here, this whole part. So we just need to apply this operator on this whole part. Therefore we can write here as this one, negative 4t sine x minus 3t minus 9t squared over 2 factorial. Okay, since this is 3t and this is negative 3t, these are going to be cancelled, but on the later stages we are going to do it. So now apply LT inverse Lx. So when Lx is applied on this function, we already know that these two terms will vanish, therefore only this term will be differentiated twice with respect to x. Therefore we are going to get negative 4t, okay, this will be positive now, sine x times t, okay, this will be integrated again with respect to t. So here we get t squared over 2 factorial, and then we apply this term negative 3 LT inverse. So negative okay, this negative and this negative is positive, so it's positive, and 4 times 3, it's 12 t squared over 2 factorial, and this is sine of x, and then positive 9t squared over 2 factorial, then positive 27t cube over 3 factorial, right? So these terms we are going to add here, therefore we are going to get positive 4t squared over 2 factorial sine of x, and this is 12 and this is 4, so it becomes 16 overall. Therefore just write it 16 here. So this is 16t squared sine x over 2 factorial, and this is 9t squared positive over 2 factorial plus 27t cube over 3 factorial, and so on. Now we can see that some of the terms here are the noise terms basically. So what do we actually mean by the noise term is that the terms that are going to be cancelled in the series, that are going to be appeared again and again with the opposite signs, right? So here we can see some of the terms, they are noise terms, and they are going to appear again and again when we expand all of the series. So here we can see that this 3d and negative 3d cancels this, and this cancels. Similarly, this will cancel with some term here, and so on. So we are only left with this term, that is 1 plus sine of x minus 4t sine of x and plus 16t squared over 2 factorial sine of x, and so on. Therefore, if we take this sine of x as common, we are left with 1 minus 4t plus 16t squared over 2 factorial, and so on, which gives u equals 1 plus sine x times. Now this is simply the Taylor series expansion of e to the power negative 4t. So it's e to the power negative 4t, and this is the final answer for this problem. All right, so this is a very tremendous approach to solve linear partial differential equations by decomposing them simultaneously using all the operators that are involved in the equation. So hope you guys enjoy this lesson, and that's all for the time being. We'll meet up in the next lesson. Thanks for watching the lesson.